The following is taken from the book High Voltage Oil Circuit Breakers, circa 1930. On page 3 we read, "The problem of switching was non-existent in the generating stations operating prior to 1890. They were small isolated plants with a few short feeders serving consumers in the immediate vicinity of the plant. In general, their output was used for lighting, and they were shut down during daylight hours. A knife switch, circuit breaker, or fuse fulfilled all the requirements for the control of these small capacity circuits. The advent of the Niagara Falls Power Company and the completion of the plant at Niagara Falls with its record-breaking 5,000 horsepower generators presented the first real problem in switch design. Fuses and open knife switches were no longer suitable or safe, and engineers set to work to devise ways to protect the generators and feeders. One outcome of this was the 5,000 horsepower 4-pole switch shown here. The 4 poles were required for the two-phase system in use in this plant. The poles were operated by compressed air and placed in an enclosed gallery so that no operator would be exposed to the arc drawn when the switches were open under load. The switch lacked any isolation between phase poles that would reduce the danger of phase-to-phase faults within the switch itself. So, the situation was that by mid-1890s, the Adams Plant No. 1, with its 5,000 horsepower, 2,300 volt alternators, the limit of the air brake switch had already been reached. It was not suitable for circuit protection. In other words, the Adams Plant, the largest in the world at that time, had nothing that we would recognize in 2026 as short-circuit protection. In the early days of the electrical power systems, the AC load was mostly lighting. The current was only in the order of tens of amperes. Direct current was the dominant form and was used for both lighting and motor loads. Loads were in the order of a few kilowatts. Alternating current circuits, however, were soon to be in the megawatt area. In some cases, higher currents were supplied to streetcars and railroad traction motors, but even as the traction business expanded, it posed no serious short-circuit problems. DC was easy to understand and followed circuit laws in an intuitive way. One of these is Kirchhoff's laws, which are based on the concept of energy conservation. Kirchhoff's law says that the current entering a junction must equal the sum of the currents leaving the junction. That is to say, I in is equal to I out 1 plus I out 2. Kirchhoff's voltage law says that in a series circuit, the voltage drop around a circuit equals the voltage source. Ohm's law says that in a series circuit, the source voltage V causes a current to flow. That current causes voltage drops in the circuit's resistance that must equal the source voltage. In other words, any voltage applied to a circuit will draw a current I, where the current is equal to the voltage divided by the circuit resistance. These laws also apply to alternating current, but the calculations involve more than simple arithmetic. In some cases, a concept as basic as Ohm's law was not fully understood. Harold W. Buck, an eminent electrical engineer and former president of the American Institute of Electrical Engineers, who in 1894 graduated from Yale University, wrote about short circuits in the 1901 AIEE transactions. In cases of short circuits in the cables, practically no damage is done at 11,000 volts on account of the small current. He continues, at 6,600 volts, such a short circuit would undoubtedly blow the cable to pieces on account of the greater current. He appears to be confusing the short circuit situation with that of the constant power concept when dealing with the transmission voltages. In the transmission case, less current is required to transmit a given block of power when a higher voltage is used. But to assume that the higher voltage applied to a short circuit will produce less current is a flagrant violation of Ohm's law. As an electrical engineer, one must assume that Buck knew this. A check on the paper's discussion section shows that no one had called him out on it. Let's have a look at the electrical power situation at the turn of the 20th century. There weren't any electrical power systems as we know them. None of the stations shown here were interconnected. Short circuit levels were low. Distribution circuits were protected by rudimentary fuses and circuit breakers. Often the fuses were just simple links. Mounted on an open board that was made of slate or steel. Although steel made for better fire protection, it provided no protection from devices that short circuits might cause to explode. Fuses were used for lower power circuits. They need to be replaced after clearing a fault. Circuit breakers were mostly used for high-powered circuits. If properly applied, they could be reused after clearing a fault. But these were basically glorified switches. In these early days, they didn't need to be much more. In general, direct current arcs could be extinguished by drawing the arc out sufficiently. However, these devices were sometimes destroyed by the current they were attempting to interrupt. We'll have a look at how one operated. On the right is a drawing of the breaker, and on the left we see the detail of the parts. The current taken by the load flowed into the positive terminal, through the circuit breaker contacts, and out of the negative terminal. A solenoid is used to detect current flow through the breaker. How it is connected to sense the current flowing in the breaker depends on the actual breaker involved. As the current in the power circuit increases, the coil unlatches the breaker and opens it. This would generally be assisted by the use of a magnetic blowout that extended the arc and quenched it.
By the last quarter of the 19th century, electrical technology was just beginning to come into its own as a legitimate discipline separate from mechanical. But once alternating current generators began to evolve into something we would recognize today, the issue of short circuits became a serious and perplexing problem. Actually, there were several problems. The first problem was the fact that there was poor understanding of AC circuit analysis. A simple means of solving AC circuits was needed, as was a straightforward way to calculate fault levels at any point in large interconnected systems. The second problem was the failure to appreciate how much the rapid development of new interconnected generating stations would affect short-circuit conditions. Thirdly, there was a poor circuit breaker philosophy design, resulting from a misunderstanding of the dynamic of the arc formed after the opening of the breaker contacts. There was also a problem of overvoltage caused by a short circuit. This problem had been noted in the late 1880s by Professor George Forbes, but he, like everyone else at the time, had no idea what was going on. Forbes was a well-respected electrical authority who had produced the preliminary Niagara alternating design. From his writing in the British periodical The Electrician, 17th November 1893, we get a good feel for the state of short-circuit understanding at the time. Forbes said that, "It is a piece of culpable ignorance, ruinous to the machinery, if anyone should ever, on a large power circuit with alternating current, suddenly break the circuit while current is passing." What he said was correct for the time, but the tremendous level of current that a short could produce was still to be witnessed a few years in the future. In 1893, Sylvanus P. Thompson, another well-respected electrical authority, suggested in the periodical Engineering, December 1st, 1893, page 674, that the difficulties arising from sudden rushes of current are seldom experienced now. All engineers slowed their machines before breaking circuits, and main switches were practically not used. A modern engineer can only see these two statements as imbecilic, but they were made by two of the most respected engineers of the 19th century. It was for these reasons that the first large alternators at the Adams plants in Niagara Falls were installed without circuit breakers, fuses, or short-circuit protection of any kind. This according to Edward Dean Adams, writing in Niagara Power, Volume 2, page 283. In 1896, protecting devices for transmission lines were conspicuous by their complete absence. The oil switch had not yet been conceived, and there was no method known by which a short circuit on an operating transmission line of the capacity we had at Niagara could be opened without shutting down the entire system. The only overload protection we had at the beginning of operations was fuses. It soon developed that the fuse under these conditions was a menace and not a protection. The amount of power to interrupt was so large that the fuses of the day could not begin to interrupt a short circuit successfully. After this fact had been demonstrated by several sad experiences, all fuses were removed. The only alternative was to arrange the entire plant would be shut down in case of a short circuit. This was accomplished by causing the field circuit breakers on the generators on the switchboard, shown here, to trip in case a short circuit came on and persisted. It was expected that the alternator's field would be de-energized to clear the fault. That was the solution that worked in 1895, when the few large alternators in existence typically supplied a single load. 5 years later, a different story was about to unfold. In the early years, the elevated trains had been pulled by small steam engines. There had been for some time a great public outcry over the pollution caused by the smoke and flying cinders. The new electrical trains would eliminate all this, and moreover, it would increase operating revenue. In New York City, the first regular electric cars were put in operation in January 1902. It was all a very modern and high-profile operation. In 1899, construction began on the generating station of the Manhattan Elevated Railway. When completed in 1902, it was, according to the Street Railway Journal, the largest generating plant in the country. Articles in technical journals and popular magazines of the day praised this exemplar of the modern age. This station, the most advanced of its time, contained 8 5,000 kilowatt 3-phase 25 Hz 11,000 volt alternators driven by reciprocating steam engines. Modern technology notwithstanding, within 6 months of the running of the last elevated steam train, a major shutdown of the electrical system caused the disruption of commuter service during the evening rush hour of 24th July 1903. The shutdown that began in their 74th Street power station quickly involved the entire system. A frantic effort returned operation by late evening. However, just before midnight, another major system fault occurred. The trains were running again within 24 hours, but the cause of the shutdown was unknown and resulted in much speculation in the engineering press. The railroad was back up and running by midnight, but within an hour it was down once again. To make matters worse, no one knew for certain what caused the outage, and because of that, they didn't understand how to prevent a reoccurrence. Several similar occurrences followed. In the Electrical Journal of 1906, on page 176, it was reported that the Manhattan Elevated Rail Company has discarded all protective apparatus because of its giving rise to more trouble than it could prevent. This was the state-of-the-art solution for short circuits in 1906, to remove the protection. Yikes. Another article in the same publication, Experience with Grounded Neutral. We can see, on page 508, that engineers began to realize that the damage which can be produced, or rather provoked, by such an unconfined arc lasting a quarter of a second was not limited to its immediate vicinity. The arc, acting as an oscillator, gives rise to potential surges capable of weakening or breaking down the insulation in other distant parts of the system, the effect of which may be apparent at once or only after several hours or days. Under such circumstances, one breakdown is usually accompanied or followed by others. But this was only the beginning. Much more work was needed. 3 years after the Manhattan episode, Chicago's Commonwealth Edison Fisk Street plant was involved in a major outage resulting from generator burnouts. This was the first plant to employ large turbo alternators. This is to say, they used steam turbines instead of reciprocating steam engines. One of these units is shown here. As with the 74th Street station, no one was certain what caused these faults. By 1909, 7 of these Commonwealth generators had failed in a similar manner. According to an article in the 1911 AIEE Transactions, the advent of the large-capacity high-speed turbogenerators, coupled to systems containing hundreds of miles of transmission lines, made them more complex, and they took on a far more serious aspect. The experience in Chicago during the past 8 years showed an increasing severity in the disturbances due to apparatus and cable breakdowns with the growth of the stations, and therefore, apparently due to the increase in generator capacity. This perhaps can be better appreciated when we remember that previous to October 1903, the total capacity in high-voltage alternators on the system of the Chicago Edison Company amounted to 9,800 kilowatts, while in October 1911, the total capacity of 3 large stations will aggregate about 250,000 kilowatts. Occasionally, disturbances were of sufficient severity to have a widespread effect. The system was therefore divided into sections so that a fault was reduced in severity and limited to one section, leaving the remainder of the system undisturbed. In the 4 years from 1906 to 1909 inclusive, there were 7 generator burnouts, all of which caused a temporary shutdown of part of all the substation apparatus on the section to which the particular generator was connected. In practically all of these cases, the armature and turns were torn loose and the windings were pretty well wrecked. The loss in revenue was immense. There were several similar but less catastrophic cases of outages at other generating stations where there was no obvious reason for the shutdowns. 11 years later, in 1923, the short circuit problem was still a great mystery. Writing in the AIEE Transactions, J. F. Peters and J. Slepian state, "In spite of its great importance, a clear understanding of what happens in an arc and ground is not general. There is no agreement as to the magnitudes of the voltages and surges produced, and the various theories proposed call for different properties of the arc. They suggest that it might be the result of the leaping growth of generating systems in the last 20 years in the incorporating of several stations into a grid of plants. After an impressive use of differential equations, the authors developed 3 mechanisms to explain what happens in a short circuit. However, they reach no conclusions as to how to design a circuit that is not susceptible to them." The paper contains an interesting comment from no less a luminary than Steinmetz that sheds some light on its usefulness. He says that, "It is regrettable that Mr. J. Sekpian rather misunderstood the bearing of my paper, as this led him to guess at assumptions made in the paper, and as I did not make these assumptions. His discussion, being based on these assumptions, becomes non-pertinent to the paper. I never made the assumption of a linear arc characteristic." Steinmetz goes on for several hundreds of words and in the process manages to rip a new one for the authors. So it seems reasonable to assume that by 1923 there is still little progress in understanding of how to control short circuits. It would take several decades for these issues to be brought fully under control.
We have already looked at the catastrophic shutdown of the Metropolitan Street Railway. 3 years earlier, when the system was being built, an article was written in the Electrical World of 1900 on page 464. Let's look at the expectations for this system as it was nearing completion. The writer says that the designers of the electrical system appreciated the risks that would accrue were this tremendous power at high voltage, 6,000 and 6,600 volts, allowed to accumulate itself on a single fault. Because of this, the power is divided as far as possible so that the station is as safe as a number of separated generating plants. To prevent the concentration of an extremely large amount of power or danger of a complete shutdown. Unfortunately, the separated stations were not as safe as they thought. Shown here is an example of the segregation concept. Two generating stations are shown, with others not shown, interconnected in a similar manner. If station number 2 has been taken offline by a fault, its disconnect is open, and the interconnection switch is closed. This would allow some of the load on station number 2 to be supplied by station number 1. The entire load of station number 2, however, would be too much of a demand for station number 1. In a similar manner, during a failure of station number 1, its load could be switched to station number 2. Although this does allow for flexibility in the operation of a system after a fault, it does not prevent the fault. Also, the cost of having what amounts to a double system is prohibitive. It's obvious that what was needed was a circuit breaker that could successfully open any short circuit that the power system was able to deliver, and then be capable of doing it again without replacing the breaker. The oil circuit breaker was intended to solve the problem. A form of oil circuit breaker had been developed in the mid-1890s in Germany by the Braun-Bavary Company. General Electric also had a patent, and by 1897 had developed a three-phase pneumatically operated oil circuit breaker similar to the one shown here on page 541. In this figure is a drawing of a Westinghouse oil circuit breaker. There are 4 sections enclosed in brick and steel, each with an access door for maintenance. The enclosure was made as explosion-proof as was possible due to the not uncommon habit of these breakers tending to destroy themselves. The contacts of the breaker are inside what was called the oil vessel. Oil was, and in many cases still is, used in circuit breakers today. When contacts are separated under heavy electrical faults, the extreme heat of the arc vaporizes the mineral oil. On the left is an oil vessel with a completed circuit. On the right, the contacts have just begun to separate to produce a high-pressure bubble of hydrogen gas. This gas was intended to cool and deionize the arc in order to stop the current flow. Although oil circuit breakers were still being installed in North America during World War II, by the time of the Korean War, around 1950, they were beginning to lose favor. This was due to the obvious hazard of using a flammable liquid to extinguish a plasma-like arc. Sulfur hexafluoride gas breakers are now typically found in high-power applications. SF6 gas has high resistivity, and perhaps more important, it does not support combustion. But the circuit breaker was only part of the solution. Perhaps more important was the lack of knowledge of alternating current circuit theory under short-circuit conditions. To make things worse, there was also no means of recording very short-duration events. Even when the oscillograph was invented in the late 1890s, it would take several years before it was sensitive enough to record in the order of a 25th to a 60th of a second. This made it difficult for engineers to understand what was actually happening in a circuit when a switch interrupted current flow. Shown here is the normal voltage and current relationship before a short circuit occurs. The following sequence is intended to give some insight into what engineers were up against before they could see these complicated events that occurred in such a short space of time, from between 2 to 4 milliseconds. Although this diagram may seem complicated, it is an oversimplification of what is actually happening in the circuit. When the short circuit occurs, the impedance of the circuit is reduced dramatically, resulting in a large arc current. The breaker opens and an arc is drawn between its opening contacts. Although this diagram may seem complicated, it is an oversimplification of what is actually happening in the circuit. Without any means of recording this less than one cycle event, the engineer of that time had no idea of the details of the fault current. What form the fault current took was difficult to determine. The shape of the arc voltage curve gives us an idea of how complex the voltage wave is. In general, the more the current deviates from a sine wave, the greater the magnitude of the high-frequency harmonics it contains. Under these conditions, the frequency of the current in the line is complex and often produces a fault distant from the point where the short occurred. To understand this situation to the point where accurate predictions of fault levels could be made would take years. Not until the digital computer came into widespread use in the 1980s could this be accomplished with a high degree of certainty.
Give him his orders at Monroe, Virginia, saying, Pete, you're way behind time. This is not 38, but it's old 97. You must putter and setter on time. He looked round, says to his black greased fireman, just shove on in a little more coal. And when we cross that white oak mountain, you can watch your 97 roll. It's a mighty rough road from Lynchburg to Danville, and a line on a 3-mile grade. It was on that grade that he lost his average, and you see what a jump he made. Was going down grade, making 90 miles an hour when his whistle broke into a scream. He was found in the wreck with his hand on the throttle and a scalded to death with a steam. Now, ladies, you must take warning from this time now and on. Never speak hard words to your true love and husband, he may leave you and never return.